Hey everyone, and welcome back to The Deep Dive. Today we're diving deep into something I know a lot of you are curious about. We've received a bunch of documentation on startup procedures for commercial refrigeration systems.
Yeah, it's something that can seem really daunting, but it's so crucial to get right.
Absolutely. We're going to break it all down for you today using a technical document that walks us through the entire startup process.
We'll be focusing on that critical initial startup phase.
So our mission today is to extract the essential knowledge for a smooth and safe startup process, highlighting the potential pitfalls and those absolutely crucial steps you can't afford to miss. So let's get right into it. Why is this initial startup phase so important?
Well, the startup is like the moment of truth. It's when any errors that might have crept into the design or assembly process are most likely to rear their ugly heads. It's a real test of how well everything's been put together.
It makes sense. So everything hinges on getting this right. And at this point, the project documentation becomes our Bible. Right.
Absolutely. Rigorously following the established protocol and all that technical documentation is key. No room for winging it here.
Right. Yeah.
Manufacturer manuals are a gold mine of information, and don't hesitate to reach out to their technical support if you hit a snag.
Great advice. I'm assuming this stage also demands meticulous checks and measurements, especially when it comes to refrigerant charging.
Spot on. Precision is paramount at every step. From verifying connections to the exact amount of refrigerant going into the system, it's about ensuring optimal performance and safe operation.
Makes perfect sense. Now, speaking of understanding the system, we always have those diagrams in the technical documentation, right? The principal diagram.
Yeah.
How do we effectively interpret that?
The principal diagram, that's like your roadmap to the system's assembly and how it's supposed to function. To understand it properly, we need to be familiar with the symbols used, which generally follow standardized norms.
Standardized? Tell me more about that.
A standardized symbol is like a universal language for representing a component, ensuring that any qualified technician can interpret it without any ambiguity. But increasingly, we're seeing diagrams using non-standardized symbols.
Interesting. Why is that becoming more common?
There are a few reasons. Sometimes it's necessary to distinguish between two parts that look identical in the standard symbology but have significant differences in reality. Other times, it's about creating more intuitive representations, easier to grasp even for folks without extensive technical training. And then there's the convenience factor with CAD software, allowing you to use pre-designed blocks and figures. So it's always a good idea to double-check the legend and any notes in the documentation to decode these local dialects of the diagram.
Gotcha. So even though there's a standard, sometimes there are these variations in these diagrams. And what about the views? I've seen elevations, plans.
Yes, the views. Those are the projections we use to represent components and installations in a 2D graphical format. The idea is that with a sufficient, minimal, and appropriate number of views, the component or installation is fully defined. We always aim for the simplest and clearest views possible, avoiding those with a lot of hidden lines.
So how many views do we typically encounter?
Usually we use three main views: the elevation, the plan, and the profile. If the left or right profile is equivalent, we usually prefer the left one. For simpler components, one or two views might be enough.
Okay, so now we've got a handle on reading the systems map. Let's talk about what nobody wants to encounter. Errors during startup. What are the most frequent culprits?
We can group the most common errors into three main categories. First up, design errors, which aren't usually major conceptual flaws, but rather specific mistakes in the written or graphical documentation, or even in the sizing of some equipment.
What about the second type of error?
Assembly errors. Sadly, these are the most common, arising from misinterpreting the documentation or just plain mistakes during the assembly process.
And the third type? Something less predictable, I guess.
Exactly, component defects. There's always the chance that some installed element might have a manufacturing flaw. These, by nature, are harder to anticipate.
In larger installations, I imagine running into some kind of issue is almost the norm, wouldn't you say?
In medium to large installations, it's rare not to encounter incidents during startup. That's why we stress the importance of a systematic and organized approach. And above all, the absolute priority must always be the safety of personnel and the integrity of the equipment.
Couldn't agree more. So what are the directives we need to follow religiously to ensure safety and a successful process?
There are a few cornerstones. First off, the current safety regulations, including the safety regulations for refrigeration plants and installations, RIghty, health and safety regulations, and the site's specific safety plan.
The project itself also sets out the guidelines, I understand.
Of course. The technical project defines the assembly procedure and points out crucial aspects to consider. And then there are the manufacturer manuals, which are often the most detailed source for startup procedures, with a heavy emphasis on safety.
And let's not forget the necessary permits to make everything legally sound.
Right. To operate the installation, authorization from the relevant territorial authority is required. This involves submitting a certificate signed by the project director and a certified installer from the installing company. This certificate must contain, at minimum, the information specified in the model outlined in the relevant technical instructions appendix.
With all this information as a foundation, how does this translate into practice? Who defines the exact steps to follow?
Usually, the site's technical management drafts a startup protocol. This protocol defines each step of the process clearly and unequivocally. It also typically includes the intermediate measurements that need to be taken to verify that everything's being executed correctly, even establishing the acceptable value ranges. And for comprehensive tracking, checklists are commonly used, where the person in charge marks off completed steps and records the obtained values.
Sounds like a very organized way to tackle something potentially complex. Are there any general criteria we should keep in mind throughout assembly and startup?
Yes, several. It's crucial to respect the timelines stipulated in the technical project and the technical management's directives. Maintaining and improving order and cleanliness in the work area with the general cleanup upon completion is essential. Work distribution should be equitable, avoiding overloading team members with physically demanding or environmentally challenging tasks. And finally, while there needs to be planning and coordination of orders from the technical management, foreman, operators, safety and health manager, property owner, it's also important to maintain some autonomy for a smooth workflow.
Let's now delve into the specific tests that are performed, starting with hydrostatic testing of pipe networks. What's involved and why is it so important?
Hydrostatic testing is essential to ensure the leak tightness of all pipes carrying fluids before they're concealed. It's a final test of all equipment and piping at a cold pressure of 1.5 times the working pressure, with a minimum of 6 bar, according to UNE 100-151. To do this, we need to plug the ends of the network during assembly, which also prevents foreign material from getting in. Conducting these tests rigorously is not just a procedure, it's an investment in the long-term safety and durability of the system.
And after the pressure test?
We then carry out water circulation tests to check filter cleanliness and measure pressures. Finally, we check the circuit's leak tightness with the fluid at its normal operating temperature. And of course, we verify the settings of all safety elements.
You also mentioned tests on duct networks. Are they similar in their purpose?
Yes, in essence. Sheet metal ducts are also tested according to UNE 100-104, and just like with pipes, plugging the ends during assembly is required to prevent dirt ingress.
What about free expansion tests? Sounds intriguing. What's involved there?
These tests are done on installations that include boilers, once the hydrostatic and safety element tests are completed successfully. It involves bringing the boiler up to the activation temperature of its safety elements after disabling automatic regulation.
Moving on to the refrigerant circuits themselves. What kind of tests are performed on them?
Refrigerant circuits in centralized installations undergo leak tests as specified in MI.IF.01 ago of the safety regulations for refrigeration plants and installations. Notably, leak testing is not required for connecting units with pre-charged lines by the manufacturer, provided the corresponding test certificate is supplied. Any pipe or element joint containing refrigerant that will be concealed must be visually inspected and tested before covering it. During and upon completing the cooling of the installation, we visually check for deformations and that the expansion system has functioned correctly. An undetected leak at this stage can lead to significant refrigerant losses over the system's lifetime, impacting both operating costs and environmental compliance. A rigorous leak test is not just a formality, it's an investment in long-term sustainability.
All of these are plumbing tests, so to speak. But electricity is equally crucial. What pre-startup electrical checks are indispensable.
Proper functioning goes far beyond just installation and wiring. Before energizing anything, it's vital to verify several aspects, starting with the interior design of the electrical panels.
Interior design. So much to consider in there.
Absolutely. Before mounting any component, whether it's a large cabinet or a small box, we need to be clear on what we're installing, switches, contactors, relays, etc., and how we're going to arrange them most efficiently, based on the distribution and control schematics. We need to choose the enclosure type and size based on the environment, the protection rating, whether it's flush or surface mounted, for indoor or outdoor use, and the material. Even the number of push buttons, indicator lights, and measuring devices on the door can influence the necessary size.
I hadn't thought of that. What about the space inside the panel?
It's crucial to consider the usable space on the mounting plate and allow for cable ducts, always leaving a reserve volume of at least 20% around the components. That 20% is not just for future expansions. It also facilitates maintenance and heat dissipation. There's even a rough method to estimate the enclosure size based on the surface area of the most common components. For example, for switches, relays, and contactors, you calculate the total surface area in square decimeters and multiply by certain factors to get an estimate of the required panel and enclosure dimensions. On top of this, performing insulation resistance tests, continuity checks, and ensuring all electrical connections have the correct tightening torque is crucial.
Very practical. Now, a central theme in refrigerant charging. What techniques are commonly employed?
There are different types of refrigerant containers, differentiated by their capacity and valve arrangement. Some allow you to obtain gaseous or liquid refrigerant simply by opening the valve or inverting the container. Others have separate outlets for both states. And then there are dosing charging cylinders, very useful when you know the exact refrigerant weight required, as they allow for controlled charging in either gaseous or liquid state.
And how is this dosing cylinder used in practice?
To charge liquid into a dosing cylinder from the bottle, you connect a service hose and use a vacuum pump to create a vacuum in the dosing cylinder. Then you connect the hose to the refrigerant cylinder, purge the air from the hose, and introduce the liquid refrigerant into the dosing cylinder. Adjust the volume according to pressure and temperature, and then you can charge the liquid refrigerant with the system off or the gaseous refrigerant with the system running through the dosing cylinder's top valve.
We also need to be mindful of the environmental impact of fluorinated gases, right?
Yeah, exactly. We categorize halogenated refrigerants into CFCs, HCFCs, and HFCs based on their ozone depletion potential and their contribution to the greenhouse effect. CFCs like R11, R12, R115 have been banned since 1995. HCFCs like R-2 are being phased out, and HFCs like R134A, R141B, while not ozone depleting, are potent greenhouse gases. There's an ongoing protocol for the progressive substitution of these gases in both maintenance and new equipment.
I understand there are also refrigerant mixtures. How do we work with those safely and efficiently?
It's important to distinguish between pure refrigerants and mixtures, which can be azeotropic or non-azeotropic. Azeotropic mixtures, starting with 5, like R500 or R502, behave like pure refrigerants and can be charged in any state. Non-azeotropic mixtures, starting with 4, like R404A, R407C, or R410A, however, should always be charged in liquid form, as their components behave differently in a gaseous state. These mixtures exhibit a glide in temperature at the same pressure between the liquid and gas phases, which can range from 1 degree C to 7 degrees C. This glide means that during evaporation or condensation at a constant pressure, the temperature of the refrigerant changes within the heat exchanger, something to consider during system design and troubleshooting. It's crucial not to simply replace one refrigerant with another without considering the equipment's specifications, like pressures, temperatures, and compressor oil compatibility. Sometimes replacement refrigerants are used for older equipment with banned refrigerants, but this can lead to a slight performance decrease and often requires changing the compressor oil to a compatible type.
Once the system is charged, how do we verify that everything is working correctly? You mentioned reading and comparing parameters. What tools do we use for that?
To evaluate operation, we need to measure and compare the system parameters with the expected values. Service manifold gauges are essential tools for measuring operating pressures, performing refrigerant transfers, and carrying out system evacuations. These gauges have different scales for pressure and temperature, and manifold gauge sets usually incorporate valves for manipulating pressure. There are even advanced models with integrated vacuum indicators, which is very handy.
And what if the parameters we measure don't match the expected values?
Initial adjustments should only be made after validation with the technical management or maintenance manager. Any modifications must strictly adhere to the manufacturer's specifications and with all necessary safety precautions taken. It's crucial to remember that in a complex system, any change to one setting can have unforeseen effects on other parts of the system.
Finally, once everything seems to be working as it should, how do we confirm that the system is ready for normal operation?
An installation certificate is used to authorize startup. But beyond the paperwork, the reliability and lifespan of the system depend heavily on the level of contamination, moisture, and non-condensable gases present in the refrigeration cycle, as well as the leak tightness of the design and construction. Good leak tightness reduces leaks and contaminant ingress, contributing to more efficient and environmentally friendly operation. All actions during startup must prioritize safety, environmental protection, and compliance with current regulations, including completing the commissioning report for legalizing the installation.
Coming back to parameter reading, you mentioned pressures and temperatures. Are there any other key parameters we should measure to verify proper functioning?
Yes. Reading pressures at different points in the circuit is fundamental to detect leaks or equipment failures. Comparing the temperatures measured at various system points with the design temperatures helps pinpoint the origin of potential problems. And if electrical system issues are suspected, measuring voltages, currents, and conductor insulation is recommended.
Let's talk specifically about the pressure leak test. How is it conducted correctly and safely?
This test provides valuable information about the overall system's leak tightness. It's imperative to use only dry nitrogen for pressurization, never oxygen or compressed air. The maximum test pressure should be 10 bar on both the high and low pressure sides. The procedure involves pressurizing the system with dry nitrogen, closing the regulator, and observing if there's a pressure drop on the pressure gauges, indicating a leak. Some leaks might be audible, and all connections should be thoroughly checked with soapy water to see if bubbles form what's known as bubble testing. If leaks are detected, they need to be repaired immediately, and the test repeated until no pressure loss is observed.
After passing the leak test, the next crucial step is evacuation. What's the main goal of this process?
Evacuation aims primarily to reduce non-condensable gases, such as air and nitrogen, and remove any moisture that might have been introduced during assembly. The target is to reach a vacuum pressure of approximately 0.5 millbar or 50 pascals, which translates to about 375 microns. Ideally, we evacuate from both the high and low pressure sides of the system if possible, and it's crucial to measure the vacuum pressure directly at the system, not just at the vacuum pump, to ensure the specified vacuum level is achieved. For efficient evacuation, using short, wide-diameter hoses like 38 is recommended, as this significantly reduces process time. Some manufacturers even specify much lower vacuum levels, requiring the use of even wider and shorter connections between the vacuum pump and the system, as standard 14 flexible hoses can restrict flow and don't provide sufficient sealing.
And finally, we arrive at the actual refrigerant charging. Any special precautions to keep in mind at this point?
It's crucial not to run the compressor without refrigerant or under vacuum, as this can severely damage the equipment. If the system's filling capacity is known, liquid refrigerant can be charged on the high pressure side with the system at rest and under vacuum, using charging cylinders or charging scales. If the exact charge amount needs to be determined, initially only enough refrigerant is charged for the low pressure switch to respond and allow the compressor to start. Generally, charging around half the nominal amount is sufficient to operate the compressor safely during the initial charging process. We always need to accurately measure the amount of refrigerant introduced into the system and avoid charging large quantities liquid refrigerant into the low pressure side to prevent liquid hammer in the compressor.
After completing the charging, what are the next steps to ensure a successful startup?
After charging, it's imperative to verify the adjustment and correct functioning of all safety and control devices in the system. The system should run long enough to observe stable conditions, during which we should record temperature and pressure values at various points in the circuit. Additionally, it's essential to clearly and permanently label the system with the actual data, the type and amount of refrigerant charged. Finally, after disconnecting the gauges and hoses, a final comprehensive leak test should be performed, using soapy water and/or an electronic leak detector, paying particular attention to common leak points like damaged nuts, service valve, packing, access fitting, mounting, poorly brazed pipe joints, corroded evaporator end bends, rubbing tubes, and cracked brazed fittings on ferrous material.
We've covered a ton of ground today. Could you briefly recap the key takeaways about starting up commercial refrigeration equipment?
Of course. Startup is a critical process that tests both the design and proper execution of the installation. Given the inherent complexity of these systems, it's expected that errors may arise. A meticulously executed startup is vital to ensure the safety of personnel and the integrity of the equipment, as well as to guarantee optimal and efficient long-term operation. The startup protocol details all the necessary steps and records to be kept. And as we've seen, the accurate measurement of key parameters and attention to detail during each phase of this process are paramount to success.
A meticulous and well-documented process seems to be the key to avoiding costly mistakes and ensuring the efficient operation of commercial refrigeration systems. Expert, thank you so much for this in-depth and detailed deep dive.
Pleasure was mine.
And to you, our listener, thanks for joining us on this deep dive.
Now, for you to continue pondering this topic, considering the increasing focus on energy efficiency and increasingly stringent environmental regulations, how do you think future startup protocols for refrigeration systems might evolve beyond the procedures we've explored today? We leave you with that question. Until next time.